since I'm just introducing folks, I have slides that explain more about the theme and what we're talking about today that folks can refer to later. So I'm going to go through them fairly quickly and get on to the business of what Joe and Alex are working on. It's taking my slides a moment to pull back up. So as Richard probably introduced but didn't realize he wasn't being transmitting, they need to validate their code for this Zoom effort. We are talking about ice sheets and how we understand how well we know them in our models, how well our models are doing. So just briefly, of course, we sit within the realm of reality of the universe of physical things. We have errors associated with observations, modeling, and discretization, and we want to make decisions based on observations, theory, and models. And so this is a schematic from Odin et al., which shows the sort of space of where we're playing. We're looking at how well our models are doing, knowing that we have some errors and imperfect things, and still being able to learn a lot. So just some terminology that folks in the talks will be using. Again, I'll go through these quickly. We want to know about confidence, how well we can rely on these models that we're developing. Insight, understanding the true nature. This is where evaluation of the models comes in, and it's designed for model developers and users. We want to talk about credibility, which is how well we can believe and trust our models. That comes in with reproducibility and discoverability, being able to access model results and being able to reproduce them so that the community has buy-in. And that's for everyone who uses those models and depends on them. Now we talk about today a lot of verification and validation and uncertainty quantification. We won't so much talk about UQ today, but it's part of the big package of how well we understand our models. And I refer you to a paper by Joe and his collaborators developing the toolkit. He does have an introduction where he explains all these terms and how they're sort of understood within the engineering and scientific fields. Just quickly, we want to talk in general about software verification, numerical verification, performance validation, and physical validation, which are different parts of V&V. And specifically, we want to focus on the physical validation. Are we using the right physics? What is the comparison to observations, and how well are we doing at actually including the right things in our models to do a good job of representing Earth? So specifically, to do a good physical validation, we want to compare to all the available data to assess model quality. We want to look at historic and present day state of the ice sheets. We want to use remotely sensed, in situ, gridded, and reanalysis data. We want validated regional models as well because they provide more insight for our global models. We want to know the uncertainty and spread in these observed quantities. It's very important for modelers to know that, and I think Alex will touch on that a bit more. And we want to increase the data availability. Anything that's available, we want modelers to have access to and understand so that they can include that in understanding the state of ice sheets and how their models are doing. Now, there's some concerns when we include observations. Ice sheet data is hard to access, to gather, to process. It's expensive. There's a short time record of data collection that's been going on for ice sheets relative to, say, the atmosphere. It's a hostile environment for instruments and scientists. These model and data are not typically co-located, so we have to understand how to interpolate one from the other and have maps and masks and all those terrible things we spend most of our lives doing. The size of data for comparison is also becoming a big computational challenge. It's great we have more data, but we have to store and access that quickly to do our evaluations. Practical concerns on the modeling side, there's no future data, obviously, so we can't validate our models in the future. We have to use the past and present. Past ice sheet changes predate directly observed information, so we have to do a lot of inference and algorithmic work. Model data do not contain variables that relate one-to-one to observations. Sometimes we have to do transfer. What the satellite reads is not necessarily what our models produce. Model grids, as I mentioned, don't match observed ice sheets extent or data, so we have to match those up, and the size of data sets. So our goal as we move to the next speakers is thinking about how models and observations combine to enhance our understanding of ice sheets. So it's a synergistic interaction. It's symbiotic, in fact. Models and observational scientists need to connect a lot more and understand what each other are doing, and that's how we can improve both. So now moving on to the next, I'll let Richard do the introductions, but we have these two talks to help us sort of think in this sort of idea of models and observations interacting with each other. One example you see here in the picture is one of the complexities. This is a recent paper by Aaron et al. Looking at the difference when you compare models, you have to compare the grids you're looking at these on and different different observational data and what that means for what you want to do when you compare models. Okay, with that, I will unshare my screen. If there are any brief questions about the just general nature of things, that's fine. Otherwise, we can save our questions for the speakers or afterwards.
Thanks very much, Kate. So we will move on to the next speaker unless there's a quick question. Oh, go ahead. Oh, sorry, let's just go on to the next speaker. Joseph Kennedy is a computational scientist in glaciology at Oak Ridge National Laboratory. He will be speaking on verification and validation tools for ice sheet models, recent development, and continuing challenges.
Okay, can everyone see my screen?
Yes.
Yep.
Okay.
Yeah.
So I'm gonna, thanks for the introduction. I'm gonna stay pretty high level in kind of the concepts around like how you would build a tool for verification and validation. And I'm hopefully gonna demonstrate 2 of the tools that we've developed here at DOE, and one of them in partnership with NASA. But when we think about developing, so first I should make sure I acknowledge everyone. This is a big, large collaborative effort. All of these tools have taken a lot of work by a lot of different people across many different institutions. DOE has primarily funded most of what I'll talk about today, but we've had some collaboration with NSF, and one of the tools I'll talk about has a lot of funding and collaboration through NASA. When we talk about assessing models, the first thing you would think about is how you would gather the data. And there's a lot of data out there. The observations come from many different types of data. You'll get satellite, remote sensing, field work, like from field campaigns. So for ice sheets, actually going out and doing stake measurements and all kinds of fun GPS and all that stuff that Tim especially knows about. And then we also have some laboratory experiments, especially in the fern realm, when we're talking about ice sheet models. And these all get reported in journals in different data formats with and often without metadata. Sometimes to understand these observations requires directly communicating with the scientists and understanding what happened in the field, why data looks a certain way. When we get into like satellite remote sensing, as Alex will talk about, things get even more complicated in terms of like understanding the actual observations and how we would relate them to models. But what this ends up is we have a massive essential swamp of distributed data that's located all over the internet, some of it not even on the internet. And we're talking multiple petabytes of data. NASA's EOS DIS right now has over 9 petabytes of data, and that's just one data center. When you go fishing in your swamp for data, you'll often encounter some, you'll pull in some boots that are a problem. So you'll get the response, the data is available upon request from the author, but the author is no longer in science. The author might be dead, especially if you're looking at older data. Sometimes the analyses were done by graduate students in groups, and that graduate student has moved on. She's no longer even in science, and nobody knows how to reproduce what she did. Other people are often afraid to share, especially their scripts they've used for analysis, because they are unclean or messy and maybe embarrassing on some level. And then if you look at data that's been published and is available, often you have to go through a step of registering with their sponsor so the sponsor knows who's using it. And that creates a lot of challenges to making an automated assessment tool, or you just can't find the data. And so as we go to think about this assessment, we have these big problems of like, how do we get all the data to the model data, or how do we get the model runs to the data? And then when you think on the modeling side, which is where we sit here at Oak Ridge, there's a lot of issues with MAR model grids versus the observational grids aren't necessarily synchronized in time, space. The projections are different. Sometimes you don't know which projection a data set used to report their variables. Variables aren't always directly related. What we use for forcing of a certain part of the ice sheet model itself may not be directly observable. So you have to build that up from available observations. And all of that requires expertise, often very, very specialized expertise in that particular measurement. I think mass movement from like the GRACE satellite and how we would interpret mass changes from GRACE satellites to ice sheet mass changes is especially complicated and requires this very specific amount of knowledge in that area, dealing with mathematics, numerical, harmonics, and whatnot. And then models sort of go through the same setup of like gathering data and all that kind of stuff just to set up the initial setup for the model and then to actually run the model. And so you need a lot of data not only to set up the model, but you need a different set of data to then build up your kind of validation database. And then models are annoying because they change a lot. They're developed out of these small functions that we've taken from a mathematical model and we've turned into a numerical model that we've then coded into a computer model. And they're made of all these different little pieces, and testing those different little pieces take various levels of effort depending on their complexity. And as we change and add features to the model, we want to continuously understand how the model is changing in relation to what we want to do with the model. That is, how have we improved the ability of our model's representation of a particular type of physics? Are we good at calving if we want to look at calving laws? Are we really good at just getting the overall mass balance of the ice sheet for sea level predictions, that kind of thing? And to really test a model as it develops requires some level of automation. So when you're building a new feature and you might want to do these low-level testing that are really quick to do as you're building the feature, and as you integrate that feature into your development branch, you'd want to do kind of a wider level of moving beyond verification into full validation. And then when you actually run the model to do predictions, you really want to have a well-validated model. You really want to understand the physics that are going on in there. So when we talk about different toolkits to do that, there's kind of two different ways to think about how to confront a model and an observation. Because observation data are really big and often need specialized knowledge to use them, a lot of tools will say, okay, why don't you run your model and send us the model output, the model data, and bring it over to the observation space, which is what the NASA CMCT, the cryosphere model comparison tool, does. And that's a web-based interface. The analysis environment, all of the comparisons and everything are done by NASA experts in that data that you're comparing. They're looking at GRACE and ISAT type data. That does require a little bit of trust in that I know that they set up their analysis well and that they know what they're doing and that kind of stuff, but it's very opaque to me what's happening as a modeler. I have to get my data to them. That's a whole different server. This tool, you upload the model data, and so you need the model to be very conformant to a specific structure so that they understand the grid structure, they know where the lat longs are, all of this parts of the data so that they can actually use your model data for the comparison. And then after they do the comparison, they email you a link to then download the data. On the opposite kind of end of the spectrum, you might decide instead, why don't we pre-process all the observations so that our model, into a way that we can compare directly our model to the observation, so that you take the observations from all the different satellites and field work and all that kind of stuff you want to do, pre-process it so it's already built into the grid structure of your model, and then you can do direct model to observation comparisons. And that's sort of what LIVVKit, the other tool I'll show, is designed for, is that we're going to bring all of the observations, it's all pre-processed to you. You can run it in your own modeling environment so you know that your environment and the analysis environment are the same. That does require the model user to set up their own analysis environment, which should be easy, but can be complicated. We also have to rehost a lot of observational data. And there's various ways of doing that and then moving that observational data onto a machine. Right now we're using get large file support with some other tools, but there's a lot of different ways to do that. And then both of these tools will produce results for you in terms of figures and some metrics that you can look at. LIVVKit produces a portable website that you can then rehost online. CMCT just sends you a tarball of figures. So I want to kind of show what they look like, and I'm hoping. So this is the CMCT website, and it appears to be down. So I can't actually show you this tool, unfortunately. It was available this morning. So let's let it chug. In terms of LIVVKit, I can show you that. This is the analysis results that Liv produces, comparing a ton of ice core data compiled by Cogley and Bales and the PROMICE program. So it's ice core and ablation stake measurements, essentially surface mass balance measurements over time. There's also some ice bridge transects just from the 2013 and 14 season. And so this is kind of a toy comparison. The model isn't trying to be representative of 2013 to 2014 or anything. It's just a model output from kind of a modern-ish day simulation. But you can see there's a ton of data locations. The white lines are the ice bridge transects. The blue dots are surface mass balance stake measurements, and they're scaled by the number of years we have representations on there. It kind of gives you a good context of what you're actually seeing in the figures. And you can kind of go through all these different analyses and look and see how well your ice sheet is doing. Very quickly, if you look at these two figures, you can see that so this is the observations versus elevation in terms of surface mass balance at all those locations. And this is modeled surface mass balance versus elevation. And you can see there's a huge bias in terms of the model versus the observed surface mass balance elevation trend. So these kind of things allow you to look at your model really quickly and detailed and figure out what's going on. And a part of the LIVVKit project was to make sure that all of this is given to whoever's looking at it who might not be an expert ice sheet modeler a lot of context. So there's a lot of figures to find, or a lot of references to find all the data and how the data was used, and then also a quick explanation of the kind of things. And there's a bit to poke around with. You can click that link in the presentation if you download it later and play around with this website. But that kind of gives you an idea of what output you're getting from these tools. And so LIVVKit is designed to be run really at this feature development kind of level. We want to be able to, and release level, be able to give it to someone and say, hey, you've changed your model. How much did that affect the physics in the model? And how well are you reproducing the world? Let's see if CMCT, nope, it's gone. So I can't show you CMCT, unfortunately. But that link in the presentation will allow you to go through it. And the DOI here is the paper that describes the tool. And there it is. So when we think about these two different ways of looking at like building a verification and validation tool, there's kind of two aspects I think that's critical to look at. Like CMCT is, hey, we really want to we are the experts at this data set, GRACE data or ISAT data. We should be doing the analysis of that observational data. We can add observations as they come in. So that's entirely the scope around that model is validation to model with their observations they know well. That's gives you a lot of benefits in that experts control the analysis. They can update it. They have a little bit of, you only have to move the specific data you want to analyze at that time to them. And they can be very clear about how the model data needs to look. So it's easy for them to analyze. The challenges associated with that is it's really hard to integrate into a development cycle, because when it's down, I can't do a comparison or show it off. When I want to analyze a model run, I have to rely on this slow data transfer to upload sometimes gigabytes of model data to them over the website. And then I have to then download sometimes gigabytes of data to get it back. And I don't really know what's going on other than I trust NASA to do a good job with their data. On the other hand, LIVV is kind of a package that's designed to really tackle all four aspects of verification and validation. We really want to be able to verify the model, look at the performance of the model, make sure the software is built and running right, and also validate it to different things. So it's a much larger scoped project. Some of the benefits of that is that we can be very open and community driven, trying to allow people to bring in their analyses and add them to our package. We can integrate directly into that development cycle so that there's rapid testing of the model as it changes. And we can use maybe some more sophisticated data transfer tools to move all that observational data, and we can customize the types of analyses we're doing depending on the modeling workflow. But it requires a higher user burden in that they have to set up their analysis environment. And there's this weird catch-22 is people really like the idea of LIVVKit, but if it doesn't provide the functions they want, they don't really want to use it or build in that function until it's usable for them. So we get this, oh, I'd love to use it, but it doesn't do this yet. It's like, well, help us build that in. Well, kind of back and forth going. So building that initial community is hard as a community-driven project. I think that kind of gives you an idea of, like, when you're thinking about building a tool for V&V, kind of the aspects of what you would want to look at. I don't think it's not really a competition. It's a decision, like whether you're moving the models to the observation or the observations to the models and how you build your tool. It's more of what's the scope of what you're trying to do, who's going to use the model data, the data itself, and kind of what, and those questions are what really should drive the approach you're doing. In terms of like making this process easier for people developing the tools, for people who provide the data, I can't stress enough how important clear and descriptive metadata is. Following community conventions like CF conventions makes my life 10,000 times easier. I immediately know exactly what that variable is describing. It's very easy to incorporate into other analyses. Descriptive data formats like NetCDF, HDF5 allow the metadata and the data to live together. I highly recommend using those kind of things. And publish the data in data center data warehouses that allow other tools to access them through an API, those kind of things, so that we can really tie them together and we don't have to break out of kind of our workflow to get to your data. One of the things that is hard often is sponsors tend to require registration, and that means that we can't just automatically rehost the data. Everyone who wants to look at that data would need to go to the website and register themselves, then download it. And then we can automatically post-process it and whatnot, but there's this like extra step. So sponsors that don't do that, their data can be integrated a lot quicker and easier and cleaner into these kind of tools. They do that because they want to understand who's using the data, and in life sciences, there might be some actual issues with ethics involved. In natural sciences like we are, I think that it's a better practice just to publish openly on these data warehouses. For these tools, really, like especially CMCT, it'd be great if they expose an API so LIVVKit could also use it and direct people there. Some way to automatically upload the data by a modeler from their modeling environment instead of having to go to a web browser and move it off of their compute machine onto some machine that they can then upload to the web browser. Releasing the analysis code goes a long way to helping people understand what's happening behind the scenes. So everything in LIVVKit is all open. You can see exactly what's happening. CMCT has described it very well in a journal article, but the code itself isn't open. So there's a higher level of trust there. But they're also the experts in that. So that's a fair level of trust. And then just placing DOIs on data and model results and all of that kind of stuff. There's a lot of ways to do that now, and I highly recommend doing it. And I've linked a few upcoming solutions in the community for helping to build these kind of tools that you can check out later. I think that sort of covers what I wanted to talk about, which is just that building a tool like this is complicated and it's really hard. And as a international community, we can do a lot of things that make these kind of tools easier by kind of helping each other. And then next, Alex is going to talk a lot about the actual data quite a bit.
Thanks very much, Joseph. That's, from a NASA perspective, it's a little bit provocative. You indicated that they're not in competition, but they do similar things by different means. Is it possible that should one choose one over the other, or should one use both validating tools?
I think it sort of depends on who you are. As a model developer, like if you're actually really in there developing the model, adding new features, I would personally, from a kind of high level V&V credibility standpoint, recommend using a tool like LIVVKit. It doesn't have to be LIVVKit, a tool like it.
And then as you gain more confidence, then you would
yeah, but as a model user that's using a released version of a model and you're making a run, you could use LIVVKit. That might be more complicated for you as not a developer to do. So tools like CMCT are great for production runs or user runs where you're not really developing the model, but you're actually just using a model that was already developed. They both have their space in the scientific community, and I don't want to imply any sort of competition between them. And like I said, if we're working behind the scenes a bit with CMCT to allow them to open an API so that Liv could call it directly. So these tools can work together cohesively as well.
All right, thank you. As I said, time is tight. Let's just take a couple of minutes for any additional questions. Does anyone have any questions for Joseph?
Hi, Joseph. This is Renu Joseph calling. So one of the questions I had for you is just to get a sense of how many users there are for, if you can say, for CMCT, and how many people have, how many groups have used LIVVKit. Do you have any
data
about that?
Mm-hmm. So CMCT, I don't know because that's at Goddard, NASA Goddard, and I don't have any usage statistics from them. I forgot to ask ahead of time. For our tool, I know that it's integrated into the DOE's E3SM analysis environment. It's a production kind of code for that, so it's used a lot in our world, essentially, that we're developing it for. I also know that Bill Lipscomb over at NCAR uses it quite a bit, actually, for CISM. And I've had 3 or 4 other people from different areas email me with questions about the tool, but because I'm an open source tool, it's sort of hard to see who's using it, who's not. I know someone in China has forked the tool, but it's hard to really, so this is why sponsors require registration, right? It's because it's really hard as an open source tool to understand how much it's being used in the community. But quite a bit around the world, at least for where it's at now, I think.
Thanks. And thanks for bringing in CMCT too, in terms of the presentation. That was very helpful.
Yeah, I really wish I could show it off. It's a cool tool.
Can I ask a question too, Joseph?
Yeah.
This is Wilbert from Los Alamos. So last month we had a presentation of the iLamp software, which is also being developed at Oak Ridge.
Yep, about 4 cubicles from me.
What?
Yeah, about 4 cubicles from me.
Okay, so I was interested to hear to what extent are these your tool and their tool being developed in parallel, or how much overlap there is.
So right now there's not any direct like code overlap between the two. There's a lot of high-level discussions about how you would do the tool. I've taken, especially, iLamb's kind of like 10 years ahead of us in a lot of respects in terms of developing a community around it. That's a tool that's really well respected in the community, has a lot of users and a lot of data because of that associated with it. So we're taking a little bit more of a comprehensive approach with LIVVKit. iLamb's really only validation as well. We're trying to handle some verification level as part of the tool. So there's a lot of discussion. One of the things that they're really good at is handling data from different models really well. And so I'm actually working with Nate to kind of incorporate some of iLamb's functionality into Liv. Then that may actually be using iLamb's code directly. So we're not working on it together, essentially, but we're working in parallel and helping each other along the way.
Can you remind me the difference between evaluation and verification?
Yeah, so verification's really, the two aspects of verification is best summarized with like, did I do the math right? Did I take my conceptual model and turn it into a numerical model well? That is my code converging at the rate it should be? And those kind of tests. And then did I take my numerical model and turn it into a computational model well? So did I actually represent that mathematical function in the code the way I thought I did? So verification is very low level mathematic programming sort of based. Validations where you're looking at observations and trying to make sure you made the right physical model.
Great, thanks.
Yep.
Okay, so I'm sorry for the tight schedule here, but we'll try to get the 2 talks in before 4, and then we'll see how much time everyone has for additional questions. But our next speaker is Alex Gardner. He's a research scientist in the Sea Level and Ice Group at NASA Jet Propulsion Laboratory in the California Institute of Technology. He'll be speaking on observing ice sheet change from space, current status, and future outlook.
Yeah, hi, thanks. I'm just going to get this up and running here. Give me 1 second.
Hi, Alex.
Hi. You can hear me okay?
Yes.
Okay, fantastic. And you can see the screen okay?
I can see your slide, yes.
Fantastic, because I can't see any of that. Okay, great. I'm just going to follow up very much from an observational perspective, highly biased to the satellite observations, and just kind of give everybody an overview of what we can do well, what we have done well, what we're going to do well, and what's coming up in the future here. So I'm glad to see an observationalist included in the discussion, because I think that's really important, and we should increase communication. So what are the key properties that we're measuring well from space? There's actually a relatively limited number of observations that we can collect to help validate ice sheet models. The key ones are ice sheet elevation, ice sheet mass change, surface melt detection, surface velocity, surface reflectance, ice sheet extent, and position of grounding lines. The nice thing about ice sheet elevation and ice sheet mass is those two are cumulative variables. So if there's an anomaly away from equilibrium, those two measurements accumulate with time. And so those are really the most trusted metrics to do validation with. Okay, I am only going to talk about ice sheet elevation, ice sheet mass change, surface melt detection, and surface velocity. And I'm going to go through this relatively quick because I suspect that most people are familiar with this stuff, and I'd rather talk about kind of what's coming out next. So elevation change, we've had radar altimetry. Conventional ocean radar altimeters started really in the early 1990s. That's an invaluable data set for looking at how ice sheets have changed, but it requires a lot of skill in understanding the data and trying to make that something that's usable for validation of ice sheet models. Then we also have NASA's laser altimetry. We have ISAT-1 that was up between 2003 and 2009, and ISAT-2, which just launched a couple weeks ago. And then we also have a deluge of stereo imagery coming in, which I'm sure people are going to start using for high resolution validation of ice sheet models. Okay, so what are the big caveats? The big caveat is that surface elevation is not directly translatable to anything that's out of a current state-of-the-art ice sheet model, and that's because most of those models, or all of those models, don't account for firm densification, which introduces a vertical velocity that's not related to mass. And so these measurements of elevation have to be corrected using the firm models to generate estimates of mass change, and then that's used to compare against the models. Now there's actually not a lot of, despite years and years of collecting data from space, there's only one time record that I'm aware of that's a publicly available history of ice sheet elevation change, and I'm not sure how useful that product is, but I'm waiting to hear some feedback. For static elevations, we have Arctic DEM produced by Ian Howitt out of the University of Ohio, and REMA, which was also Ian Howitt and University of Minnesota. So I provide the links if you want to go explore, find the data, go for it. Okay, mass change. Mass change has taken a while for people to be able to understand how to work with the data. It was kind of saved for geodesists, probably the first almost decade of the mission. But the data's really matured, and I encourage you all to go find what's called MassCon solutions, where they provide the mass change localized to 3 degree or 1 degree cells on the Earth. And there's a huge amount of modeling that goes into that to generate those grids, and they're very robust. There's now kind of 3 flavors of MassCon solutions that you can get out there. There's the JPL MassCons, CSR, and the Goddard Space Flight Center. Very valuable data, easy to work with. Surface melt, so passive microwave has given us the longest record of ice change. And what it gives us is it gives us a binary index of whether there's liquid water present on the surface or not. And one of the complications of this is presence of surface water does not necessarily mean melting. And so you have surface water that's retained in the snowpack even when active melting is not taking place once the snowpack is isothermal. So relating that again to model variables can be difficult, but it is an indication of how much melt is occurring. And then surface velocities. We have surface velocities mostly from radar. That's the data that's available, but there's a lot of new methods being applied to optical imagery. So the Landsat, Aster, Sentinel-2 time series, and I'm going to show you some of that kind of later on here, what we're able to do with that. The big data sources for that are NASA Measures, the GIMP project, that's for Greenland, and then the NASA Measures Antarctica. Okay, so what can't we measure well? We can't measure precipitation all that well over the ice sheets. A lot of the methods that are good at retrieving precipitation over water don't work well over bright ice surfaces. Clouds and ice look very similar in a lot of the different wavelengths, and so it can be hard to distinguish. And the type of precipitation that falls over the ice sheets is very challenging to retrieve. So there has been some luck with things like CloudSat, but any precipitation that's coming out of a remotely sensed product can be highly biased and difficult to work with. I was involved with a recent study looking just generally at Arctic precipitation, and initial comparison with GRACE estimates, which we place a lot of trust in, show that that all precipitation measurements have large biases at high latitudes. So that's always going to be a challenge for the near future. Melt magnitude. So despite being able to measure binary melt, whether melt is occurring or not, we are not able to estimate the magnitude of melt or active melting. So that's also a challenge. Sublimation, we're unable to measure from space. Runoff, so if melt occurs, how much of that water is retained within the ice sheet and does it percolate down and then refreeze, and how much actually runs off. That's a very difficult measurement to make as well. Ice thickness. Now, ice thickness, we can get line profiles from airborne missions, but as of present, we don't have any orbiting ice sounder. And so the data coverage is limited. And there are new methods that have come out, things like bed machine, and they have helped greatly in producing improved ice thickness. But it should be kept in mind that as soon as an observation is missing, it's used in bed in a mass conserving sense. And so wherever there's large biases in the modeled surface mass budget, you can also have large biases in the modeled ice thickness. So that's still a limitation. And then basal properties, we can't measure basal properties from space, and ice viscosity. So there's numerous measurements that have been collected. We have a relatively long time record for some of the variables, but other than velocity and binary melt, as Joe mentioned, the data is difficult to work with, requires specialized knowledge, instruments. A lot of the publications, the data is unpublished, the code's unpublished. And so I empathize with the modelers' frustrations in seeing publications claiming to have measured the volume changes of the ice sheet or some property of the ice sheet, but then not being able to get access to the data. The places you should be looking to for the higher quality data are the NASA Measures program and ESA's CCI products. And those are going to be rolling out a new version of the Measures projects. Will be rolling out over the next 2 to 5 years, and ESA is starting to publish some of their products now. So that's where there's a lot of responsibility placed on the producers of those products to generate good metadata and robust errors. So future outlook looks really good for remote sensing. We have a huge amount of data that's going to be coming available and is starting to pour online. In fact, we have a lot of data sitting on the servers that just hasn't been processed because the data volumes are so gargantuan that it takes a while to develop the code and the models to be able to work with the data. So a couple of the big data sources are the Sentinel-1 A and B. That's a pair of SAR satellites that basically get global coverage every 6 days. So we'll get very good velocity retrievals from those. And then we have a huge stream of optical data coming out, Landsat 8, there'll be a follow-on Landsat 9, Sentinel-2 A and B, so we get nearly continuous coverage from optical data. ISAT 2 will turn on its laser for the first time on Sunday, and that's going to give us incredibly precise measurements of elevation, and those will be unique relative to something like Cryosat in that the precision with which we can measure the interior of the ice sheets will be much higher, and so we can start to look at rates of change in the interiors. So places like East Antarctic will do very well there. NISAR launches in 2021 or early 2022. And there's a new measures initiative. Both the Greenland and the Antarctic initiatives were continued, and there's a new initiative called It's Live, and that's the initiative that I'm leading. I'm PI on that. So I'm going to talk a little bit about that It's Live here. Okay, so It's Live just received funding starting a few months ago, and it will continue for 5 years, and it's promised the world, and so hopefully it will produce that as well. We've really thought about the usability. We want to decrease the barrier to entry to using this data, and so we are generating global coverage of velocity and elevation changes. Everything's going to be on standardized nested grids, and so if something is produced at a different resolution, that resolution will always nest to the native grid. So they'll hopefully minimize things like reprojections. All of the code will be open source. A lot of it is already, The products will be synthesized between missions, and we will also provide our best estimate of interpolation. And so all of our data products will contain flags where you can mask out interpolated data or just use the raw data, or what we like to call the raw data. It will be produced with low latency. In some of these cases, 1 to 2 months after acquisition by the satellite, the data will be incorporated into our products. And everything is NetCDF4, HDF5 compliant, so it has self-consistent metadata. Just to tell you a little bit about the data that's going to be coming out, there'll be terabytes of, around the order of 100 terabytes of image pair results, which will just be for the nerdy data scientist that wants to go, apply machine learning or apply their own algorithms to generate robust velocity fields. But for the modelers, we'll be producing monthly and quarterly mosaics at 240 meters resolution. And those will be globally and continuing to update as the missions feed in data. The record will go from 2013 to present, but we're also going to throw in some data that we already have that goes back to 1985. And you have to work with that at the quality of the data. So it's not complete coverage data. And then for elevation change, we're providing a product that's going to go all the way back to 1992. It's going to include all of the radar missions, so ERS-1, 2, NVSat, Cryosat-2, and then it will also include the laser missions of ISAT and ISAT-2, and then it will be fully validated against the Operation Icebridge airborne data. That will be produced at about 1 kilometer resolution, and again, that's on a nested grid. And we will also be producing ice shelf melt rates, which we're receiving increased interest in. So one of the things I wanted to talk about is there's a reason that all of these products aren't available online and for free download, and that's because despite a satellite being able to measure something like elevation, it's not quite as simple as that, and that's because things like radar are sensitive to the changes in the dielectric properties of the surface, and so the elevation that you retrieve can be greatly dependent on changes in the dielectric properties, whether it be wind, melt, other things that can cause changes in the way the radar waveform interacts with the surface. But our goal is for you not to have to worry about it, but I think you really should start thinking the data not as so much a measurement, but as a modeled estimate from the measurements. Just to generate a record of elevation change, you can see that on the top right slide, that's kind of what the data looks like if you just went and downloaded it. And what we have to do on our side is we have to cross-calibrate the different missions to line them up. We have to remove the mean topography, so you're not just measuring different places on the ice sheet and assuming they're the same spot. You have to correct for all sorts of different sensor biases, correct for scattering problems, and then ultimately, because there's so much noise in the data, you have to apply some sort of Kalman smoothing or modeling methods to generate continuous records. And so there needs to be an intimate connection between how these data are generated and how they're being used by the modelers to do the validation. This is particularly concerned of places where there's lower signal or that can be greatly impacted by changes in the dielectric properties. So interiors of the ice sheets are always problematic. But after you work on this for 3 years, you can get the time series that look like this. This is still a beta product, but we hope to release it likely within the next 6 months or earlier. And so this would be a continuous gridded product of elevation change starting all the way from 1992 going to present, and will be updated. And so this will be good for validation. And then something else I just wanted to talk about, this is kind of my pet project, is velocities from the Landsat archive. So we've had Landsat imagery being collected since the 70s. It can be used for feature tracking really starting in the mid-1980s. And the data is really noisy, and so a lot of people are dismissive of it. But in this messy data, you can apply different modeling methods and data filtering methods to try and extract the signal. And this is just one example of a single glacier. This is the flow at a single 240 meter pixel location, and I'm showing velocity. And the dots are the raw measurements. So you go download those raw measurements, and your immediate reaction would be that they're useless for model validation because the noise level is so high. But if you work with the data long enough and careful enough, you can generate these records of change. And so the red line is showing the annual change, and the blue line is showing the reconstructed seasonal cycle in the glacier chain, in the glacier velocity. And so you apply heavy post-processing, least squares fits, and Kalman methods to extract the signal. And what you get is you can extract a 33-year record of discharge for the Greenland ice sheet. And that's what the movie is showing right here is as the animation plays forward, we're looking at the cumulative change in discharge. And when I say cumulative change, we're just looking at the change relative from 1985 to 1995. And you can see the cumulative anomaly growing with time. And in the bottom right-hand corner, that's actually the discharge magnitude each year and how it's impacted by the change in the seasonal cycle. And so we expect data sets like this to really be valuable for model validation. Okay. This is just a quick slide saying that we have a lot of activities going on here at JPL. I'm right next door to the ISSM people, and we're working closely to try and get, especially with the data assimilation, so assimilation of velocity, elevation, and mass change data. So we're setting up a pipeline in which ISSM can just directly read in all of the data as it's being produced at the gridded level. We also have work by Josh that is looking at paleo terminus positions and then seeing how well he can do with higher order ISSM model runs to fit those paleo extents over the last 10,000 years. And then we're also working on a sophisticated treatment of surface mass and energy fluxes, and that's because a lot of the observables that we collect from space, things like surface temperature or presence of meltwater, really requires the full energy balance at the surface to be resolved in order to be able to either assimilate or use those data for validation. So now I get to put in my one request to modelers, because I expect that most of the people on the line are modelers. So all measurements contain spatially and temporally correlated errors that impact validation. Now, the errors that are typically provided with data products don't account for these correlated errors. And it's not that the producers of these products don't want to provide them. It's just incredibly difficult to quantify the errors of a quantity that's never been measured before. And so this is a first best attempt. And so, have realistic expectations of the accuracy and knowledge of errors. It's really very much like modeling in some respects. And so, you do the best you can. You try and generate continuous observations, but you're really limited by the observational methods. And then the last request is that, that observationalists, that you try and at least work with them or understand how the data is being generated, and just have really frank discussions about strengths and limitations of the data sets, particularly with correlated error. And so what I typically see is that a data set will be used to validate a model, but we have either low confidence in that model, or we only have high confidence in certain areas. And so things like that are good discussions to have, and I guess this is a place to do that. That's everything I have for today. I'm going to exit out of full screen here if I can figure that out, and open up for any questions if we have any time.
Thanks very much, Alex. That was a terrific overview of remote sensing. I briefly had a question about some of the satellites that you didn't mention. We had a speaker, Jen Kay from the University of Colorado last week, who talked about CloudSat Calypso, which was one of the satellites that you didn't mention. Yeah. They seem to be fairly interested in using that for precipitation estimates over ice sheets. The ice sheet modelers, I know we don't use it as much. Do you find that to be a useful instrument?
I think it's in the stage. It's showing really promising results, without a doubt. But I think it's still in the research stage, so I'm not sure if anybody's quite ready to provide a product and put their name on it. But the most impressive thing with the CloudSat is it seems like the mass anomalies line up fairly well with GRACE, and it seems to outperform other approaches, methods at high latitude. So yeah, I expect that there'll be some more of that.
Okay, great. You also didn't talk about gravity. I don't know if you have an update on GRACE FO and its issues.
They just got permission to switch to B-side, so we're waiting. So GRACE follow-on has had some issues post-launch that have been very challenging to get through, and so the team has been really active in trying to solve those, and they were working on so each satellite has an A side and a B side. You hope to run the mission for 3 years and encounter an error and then switch over to the other side. It looks like we may have to switch from the A side to the B side, or in this case, we're actually switching to the A side, but in order to get the measurements. So yeah, we have been encountering some trouble.
All right, fingers crossed. Are there any other questions for Alex?
Okay, looks like everyone can go for lunch then. Well, I can go for lunch. I'm on the West Coast.
Just wait a second. You mentioned Ian Howitt. He's at Ohio State University. One correction.
Oh, what did I say? Oh, dear Lord.
You said Ohio University. They're kind of particular about that.
Okay.
And I've talked to some people here who have interest in using GeoSat to extend further back in the record.
Good luck. We've been working with the data for 2 years, and other than getting to say you use GeoSat in extending the record, we haven't found a whole lot of value yet.
Okay, any questions?
This sounds quite premature, but I was wondering, you know, from the larger, so it's not a regional Arctic or an Antarctic perspective, but from a larger global modeling perspective, there are efforts like OPS4MIP that put things in that make it kind of easier for people to evaluate their models. I don't expect it right now, but how much time would you think it would take to get products that can be put into things like OPS4MIP?
Well, the new data that's coming out is going to be, you know, ESDIS and ESDIS compliant, and it will all be on the DAX. And so I think as long as you're able to work with the DAX, you shouldn't have any trouble drawing in the data. Remember, though, that these data sets are huge. And so the question is do we move around the data sets that are static and used by all, or do we move around the unique model output? And so that's kind of something to think about as well. So I expect that shortly all of this will be on the cloud within the next 3 to 5 years, and so that shouldn't be a problem. But in the interim, we're going to suffer a bit, I think.
Mm-hmm.
Yeah, and on the modeling side, it's important to remember too that the model output now is in terabyte to petabyte range as well. So data movement is hugely problematic for the next few years until everybody gets on the cloud, I think, or at least co-located centers or good Globus connections or something to get data movement handled better.
Mm-hmm.
Okay, any other questions? Well, this was my first time leading one of these sessions. I'd like to thank the co-leads, Wilbert and Renew. I thought this was a great session, and I'd like to very much thank the speakers. I thought these were all excellent talks.
Thank you.
I think that's it.
Okay, great. Thanks a lot for organizing.
Thanks very much.